All right, I'll be presenting on statistical inference with M-Estimators on adaptively collected data. This is a 2021 paper by Kelly Zhang, Lucas Jensen, and Susan Murphy. In this presentation, we'll explore the challenges of performing statistical inference on data collected using bandit algorithms and introduce a method for constructing valid confidence regions in the setting. I'll cover the setting, the methodology, and assumptions, and then my own numerical analysis, since the authors supplied the code needed to reproduce and test the results in their paper. Let's start with some background. Bandit algorithms are a class of sequential decision-making algorithms that balance exploration and exploitation. So exploration involves gathering new information, while exploitation uses existing information to make optimal decisions. A key characteristic of bandit algorithms is that the data they collect is adaptively sampled. This means that past observations influence future actions, leading to dependence in the data. And the goal of using bandit algorithms in this setting are twofold. One is regret minimization, and this focus is on selecting the best actions within an experiment to minimize losses. But what's becoming increasingly common is that one might want to perform statistical inference on these data. And this aim here is to draw conclusions from data collected with bandit algorithms that can then inform future experiments. So this includes hypothesis testing. However, performing statistical inference in these tests on adaptively collected data presents several challenges. One of them is sampling bias. So adaptive sampling methods can introduce dependencies in the observed data. This violates often the independence assumption of traditional statistical methods. And this, in general, means the data is not IID. A problem with this is with traditional methods, it leads to inflated type 1 errors or false positive rates. Because a result of these dependencies, the variances of traditional M-estimators become unstable, and these lead to inflated false positive rates in hypothesis testing settings. Okay, so before we go further, let's define the key notation that's used throughout the paper. So they define multiple data structures. The first is contexts, which provide information about the current state of the system at each time step. Actions are the choices made by the bandit algorithm at each time step. And rewards are a deterministic function of the outcomes. So these structures define a general class of adaptive methods. The outcomes here, there are different types. The primary outcomes represent the true outcomes of interest in the experiment. These are theoretical. So they live in the population level. Potential outcomes represent the theoretical space of outcomes for every possible action. And these potential outcomes are assumed to be IID, meaning that they come from the same distribution and are not influenced by past observations. So they're essentially stationary. Then you have the observed outcome, which is a realized outcome from the specific action chosen at a given time. And these observed outcomes are not IID due to the adaptive nature of the bandit algorithm. So the observed outcomes in this case are at the data level. And we have some definitions. First, the model defines the parameter of interest as a value that maximizes the expected value of a criterion function. So this criterion function could be, for example, the negative squared loss function if we're maximizing, or just the squared loss function if we're minimizing. It could also be the log likelihood function if we're in the MLE setting. But in general, the estimator, theta hat, is the value of theta that maximizes the empirical analog of the criterion function. So this analog is based on observed data. And the objective here, the main objective of the whole paper, is to derive asymptotically valid confidence regions for this parameter of interest, which is theta star. All right. So to address the challenges of inference on adaptively collected data, the authors propose a method using adaptively weighted M-estimators. So the motivation here is to stabilize standard errors. So adaptive weights are introduced to counteract the instability in the variance of the estimator caused by adaptive policies. So the weighted M-estimator, this introduces weights, WT, into the standard M-estimation criterion function. The specific weights that are proposed in the paper are called square root importance weights, and these involve two policies. The first is a stabilizing policy, which represents a pre-specified policy that does not depend on the adaptively collected data. So a simple and common choice is just a uniform distribution over all actions. And then there's an adaptive policy. This represents the adaptive policy that's actually used to collect the data. So the specific type of bandit algorithm or adaptive algorithm that's used to collect the data follows an adaptive policy. And the square root importance, the ratio between these, is used to essentially reweight the data to resemble data collected under a stabilizing policy. So this restabilizes the variance of the M-estimator. The variance is usually just based on adaptive policy. If you're just looking at the kind of a naive M-estimator, we want to restabilize these by introducing a policy that does not depend on the time index t. Okay. So in the paper, they prove these results, but these are, I'll just point them out here. The first is the consistency of these M-estimators when you include the weights. So the estimator converges in probability to the true parameter value, which is theta star, uniformly over the space of possible distributions. So this means that as the sample size t increases, the estimator gets arbitrarily close to the true value, regardless of the underlying distribution. And then they also prove asymptotic normality. So using a central limit theorem, they show that the distribution of the estimator after appropriate scaling and centering converges to a normal or Gaussian distribution. And this property is then crucial for constructing confidence regions. So by leveraging this asymptotic normality, they construct confidence regions that are asymptotically valid, meaning that their coverage probabilities approach the desired level as the sample size increases. So this ensures that the true parameter value falls within the confidence region with a probability at least as large as the specified confidence level. This is usually set, this is usually an alpha level set at 5% or something. These properties are derived from the fact that using these square root importance rates, the covariance of the asymptotic distribution is based on the stabilizing policy that doesn't depend on time, rather than the potentially ill-behaved adaptive policy that is used to collect the data. Okay. Of course, these properties and results depend on quite a few assumptions, especially that the context, especially stochastic bandit environment, which means that the contexts and potential outcomes are assumed to be independent and identically distributed across time. Secondly, the criterion function needs to be differentiable with respect to the parameter theta. This criterion function must also satisfy a Lipschitz condition, ensuring that the changes in the parameter value result in bounded changes in the criterion function. It's essentially putting a smoothness requirement on the criterion function. And this assumption helps control the variability of the estimator. Then we have that the parameter space needs to be bounded and open. And the criterion function and its derivatives are assumed to have bounded moments up to a certain order. This ensures stability of the estimator. And lastly, the ratio between the stabilizing policy and adaptive policy needs to be bounded. So this assumption is crucial for controlling the influence of individual observations and preventing any extreme weights that could throw off or destabilize this estimator. Okay, so the authors demonstrate the effectiveness of their method through simulations. And here's the setup. So in a simple scenario, they have a two-arm contextual bandit. These are a case where there's two possible actions to choose from at each time step. And the expected reward in this case is a linear function of the context, x of t, and depends on the chosen action, a of t. And in the setting, they're looking at a special case of M-estimators, least squares estimators, which are commonly applied. And they compare two different types of least squared estimators. So the unweighted or ordinary least squares, this is the standard estimator that's usually used, or that in this case is used without any adaptive weighting. So it's applied naively. And then they introduce their adaptively weighted least squares estimator. And this uses the square root importance weights that were discussed previously. So the goal here is to estimate the parameter associated with action 1, where the indicator function selects the data points where action 1 was chosen. And here the stabilizing policy is a uniform distribution with two possible actions. And critical point is that this policy does not depend on time t. So it's, again, trying to take out the dependence in the data caused by the adaptive algorithm that's generating it. So these are the results presented in the paper. And the left panel, the histograms display the distribution of the disease statistic for the unweighted least squared or OLS estimator. And here notice that the distribution deviates from the standard normal, indicating that the inferences based on the OLS estimator is invalid under adaptive sampling. So the central limit theorem that's applied without the weighting scheme does not account for the fact that there's dependence in this adaptively sampled data. So they correct for this by introducing the adaptively weighted estimator. This is the right panel. And here the histogram shows that the distribution of the z statistic for the adaptively weighted estimator, in contrast to the OS estimator, this distribution aligns more closely with the standard normal. And this confirms the validity of and confidence regions that are derived from this distribution. So this visual comparison clearly demonstrates the improvement by using adaptive weights for statistical inference. And in this case, they're using a special type of adaptive sampling called Thompson sampling. And this is what is used to generate the regression data. Okay, So to further explore the method presented in the paper, I used the code that was provided with the paper to conduct some more simulations. So I'm essentially regenerating the figures they have here. But here I wanted to see what would happen if I varied the sample size t. So the results are shown in this figure with the first column here representing the distribution of the OLS estimator, and the second column representing the distribution of the adaptively weighted estimator. So here are some observations that I took away. The first is that the type 1 error for the OLS estimator increases with sample size. And I was thinking this is likely due to the nature of the adaptive sampling algorithm, which with less data is usually because adaptive methods balance exploration and exploitation, but at the beginning, they're usually more explorative. So they aren't exploiting any policies. So essentially, for small sample sizes, the data looks more IID. Whereas you increase the sample size, then the exploitation phase of the algorithm kicks in, and you get more dependence in the data. So when you increase the sample size in this case, this transition amplifies the time dependence of the data. And as you can see, it leads to more false positives. And in contrast, adaptively weighted estimator seems to maintain a type 1 error below the nominal level, which was 0.45%, across all of the sample sizes tested. So even small samples of 10, controlling this false positive rate. So this demonstrates its ability to provide valid statistical testing, even when there are strong dependencies in the data, especially as this sample size of 1,000. However, just from this figure alone, it is difficult to see any improvement with large samples because I'm plotting the normalized histograms. But this next figure here displays a plot of the mean squared errors of the adaptively weighted estimator as a function of sample size. So the plot here shows a clear trend of decreasing mean squared error as the sample size increases. So this reinforces the consistency of the adaptively weighted estimator, highlighting its improved estimation accuracy with more samples. Okay. So yeah, in conclusion, the paper by Kelly Zhang and colleagues offers a valuable contribution to statistical inference in the context of adaptively sampled or collected data. Bandit algorithms introduce data dependencies that make traditional inferences unreliable. Adaptively weighted M-estimators using square root importance weights provide valid statistical inference from data collected with bandit algorithms. And lastly, least squares simulations confirm theoretical asymptotic results, and that this approach stabilizes standard errors and maintains valid type 1 error rates. All right, thank you for listening.